Hello again. Moving on in Chem 30 to another type of organic chemical reaction. We're going to do substitution reactions next. I know they're third in my list, but they are the next ones in your notes. So addition is pretty logical. We took two different things, added them together, we ended up with one singular entity. Substitution is more of a swap type idea. It's a trade. It's like, I'll give you this if you give me that, right? So we start with two structures and we're going to end with still having two different products. All right. So ultimately what's happening with substitution is we're taking a hydrogen atom or potentially a functional group like a hydroxyl group, and then we're swapping it for a different functional group, right? So a switch, a substitute, if you will. Okay, let's check it out. Evidence of this sort of thing. Well, the key start of this is what I already mentioned. You'll start with two compounds and then you'll end up forming two different compounds. When you get to the last question in the assignment, it's really important that you can identify these reactions. So considering different little criteria like this makes a big difference. So starting with two reactants, finishing with two products. And that's a good hint of substitution versus addition, starting with two reactants that are added together to make one singular product. That's a key difference. Consider those sorts of things, all right? Now, when you do a substitution, the carbon atoms are still bonded to the exact same number of atoms in the reactants as they are on the product. So we're not trying to change the type of bonding. We're not forming double bonds. We're not forming triple bonds. We're not breaking double bonds. We're not breaking triple bonds. It's going to stay consistent from the reactants to the products. Another thing you can look for. Going into a really simplistic type of this, one thing we could do is take a saturated hydrocarbon, so that means it has only single bonds between carbons, and react it with a halogen. Now, I already talked about the halogens last time. Your options here are going to be chlorine, bromine, iodine, and fluorine. Those are your possibilities. And from the picture that you can see below here, we're taking methane to start, reacting with the halogen chlorine. And what you see circled in, or sorry, not circled, but in red or in green is going to get swapped out. So now in the product, we end up with a chloromethane because chlorine's been swapped out. And we now have a hydrogen halide, not just chlorine, but hydrogen chloride. It is a substitution. It is, if you like the sound better of it, it makes your brain work better. It is a switch. Okay, one takes the place of the other. Potentially, you could absolutely end up with isomers. If that happens, hey, guess what? They have to be listed, named, drawn, the whole shebang. Okay, one other thing that I'll add into this, when we're taking these long chain hydrocarbons, potentially long, and adding them to a halogen, generally speaking, the reaction doesn't happen just on its own. It needs a catalyst. Most common catalyst we use for these is UV light. Now, if you remember back to the first unit, and if you've taken biology, this is familiar too, catalysts lower the reaction energy required. They do not change the products in any way, shape, or form. They just make it easier for the reaction to go to completion. It makes it easier to get to the products. Alrighty, here's your most simplified version of this. X represents the different halogens. UV light is there. And you can see again, it is a simple matter of a swap between two different types. But I emphasize once more, man, they're slow reactions here. So the UV light helps. This is also a nice hint. Every substitution reaction will not use UV light. The ones with the hydrocarbon reacting with a halogen will. So if you ever see a reaction with UV light, your brain should go ding, ding, ding. Oh, this is substitution. It's like a built-in hint, if you will. Okay. So take propane adding to bromine. So we're adding it to a halogen, which means the UV light is definitely going to make a huge difference here. Step one is let's draw out the propane. Really simple, 3 carbon hydrocarbon. These are the ones we started with 2 weeks ago, right? No big deal. Added to bromine, diatomic, of course, as the halogen. And scenario-wise, what could happen here? Well, look at this thing. Nothing dictates exactly which hydrogen is going to switch with the bromine. So that's where you got to play a little bit. Here's one possible scenario. The bromine is going to switch with a hydrogen on carbon 2. Sure, that could definitely happen. But is there anything stopping the bromine from instead switching with a hydrogen on carbon? Well, it looks like carbon 3, but technically that's carbon 1, right? It's on the end. Nope, that's absolutely a possibility. They both are, which means, dun, 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 we have isomers, all right? Mentioned that would happen, okay? So let's look at the first scenario that I did in red. We will end up with CH3. There's no longer CH2. We're swapping out a hydrogen, so it's just CH. And then we're going to end up with the bromine going on that second carbon, and then still a CH3 on the end. One option. The next option I'll do in green is where it swaps out with the first carbon. So in that case, we have CH3. The second one is still CH2, but the last one swaps out a hydrogen. It's now CH2, and a bromine is put on there. There we go, guys. Two different isomers. Now here's a common mistake. Don't forget, there's another product. That hydrogen swapped out with the bromine. So we also have a hydrogen bromine that was produced, HBr. Two reactants, two products. To clarify, you need to name these. So it'll be this or this that's produced. The red one is going to be named 2-bromopropane. And my green one here is going to be named, it's on the first carbon. Think about how the numbering goes, 1, 2, 3. Always make the branches the lowest numbers. So this will be 1-bromopropane. You still have to name the hydrogen bromide. I will be looking for it. If you forget it, you're going to end up losing marks. Sorry, my pen's not working at the bottom here. Hydrogen bromide. So all the possibilities are named. 2-bromopropane, 1-bromopropane, and the other definite product, the hydrogen bromide, must be named as well. There we go. Isomers are formed. Both are listed. Check out the next one. This one is already an alkyl halide. Oh, that's weird. But why not? Why couldn't there be a halogen on there already? So let's start by drawing it. 2-chloropropane. So once again, we have a 3-carbon chain, but there is already a chlorine present on the second carbon. No problem. It's being added to a halogen, chlorine, which means UV light is certainly helpful to get this reaction going. Now, how is this going to look? We are going to have isomers again, guys. Here's one option. This chlorine could swap out for the hydrogen on the second carbon. Why not? There's nothing to say it couldn't. Yes, then there'll be 2 chlorines on the second carbon, but there certainly could be. Vice versa, we could have this chlorine swapping out for a hydrogen on the first carbon. Yep, isomers. It's happened again. I'm going to draw the green one first. So the potential with that one is that we are going to have CH3, CH, and CH, chlorine 2, just like so. Okay. Oops, I forgot my chlorine in my second one. There we go. So that initial chlorine, this dealio right here, is still there. Why? Well, because it was part of the original structure. The next one is this chlorine being added in, right? Or being swapped out, I should say. Not added in, substituted out for that hydrogen. Okay, next option. Let's go to the red one. With this one, we have CH3, and then we still have CH with a chlorine on top. But now an extra chlorine is going to be put on that second carbon, and then it still finishes with the CH3. Okay, similar type thing. We still have that chlorine being swapped out, and we still have that original chlorine that was there. Once again, you end up with one more product, which is your HCl, right? When that hydrogen swapped with the chlorine. So let's name that one first because it's easy and you really don't want to forget it. Hydrogen chloride. My green one there, I've got 2 different chlorines, so 1, 2 dash. Have to specify there's 2 dichloropropane. And the red one, there's 2 of them. Some of you were messing this up in your assignments. You have to write the number 3 twice because it's on 3 twice. So 3, 3 dash, again, dichloropropane. There you have it. Our 2 isomers, and then the definitive hydrogen chloride that's going to be there too. Isomers are formed. This is a substitution. Now again, that was with a halogen, which means the UV light was helpful. Well, what if we have another possible scenario? Here's another thing that could happen. You could have an alcohol that is reacting and undergoing substitution, and it's going to be with either hydrogen bromide or hydrogen chloride. This is not with a halogen, this is with a hydrogen halide, right? It's not just bromine, it is hydrogen bromide. It's not just chlorine, it is hydrogen chloride. That is a distinct difference. So in the scenario that I have here as an example, we've got methanol that's reacting with hydrogen bromide. And it's the exact same type of an idea where we have this hydroxyl group that's going to swap out for a halogen. And there's your substitution. This, of course, changes what we've got. We now have a group of carbons attached to a halogen. So we now have an alkyl halide. And think about this, HOH, oh, you just formed water. Okay, so when we do substitution with alcohols, you'll always see it with water. These reactions don't require a catalyst, so you won't see the UV light with them. How do you know it's substitution? Well, you have 2 reactants and 2 products. There's no double bonds or triple bonds formed or broken, and you can see a swap between things. Look for those sorts of little hints. Let's try a couple examples here. Propan-2-ol. So we've got an alcohol. It is a 3-carbon alcohol, and the hydroxyl group is coming off of carbon number 2. There it is. With hydrogen chloride. Hint, hint, hint. This should catch your attention right away. The alcohol is added to a hydrogen halide. So we're going to have that circumstance where the hydroxyl group is going to swap out not with the hydrogen, but with the halogen. That's key. Here's where the swap is going to occur. Okay, now this is really specific. You don't get isomers formed with this one because all that can be moved off, sorry guys, is the hydroxyl group, right? So we have our CH3 on carbon number 2. My chlorine is going to go on there because the hydroxyl swaps off. CH3 plus, we've got the hydrogen going with the hydroxyl. There's the hydrogen. There's the hydroxyl. There we go. Now, in terms of what do we have here, you have to name both of them. And yeah, that includes naming the water. I know that seems obvious, but too bad. Name all the products. That's what the questions will say. That chlorine is on carbon 2, so 2-chloropropane. No isomers. The chlorine can only go on carbon 2 because that's where the hydroxyl group was that we swapped off with. One more example before you can get into a bit more of the assignment. This one, cyclopentanol. So we have a 5-carbon cyclic structure with a hydroxyl group coming off. It doesn't matter which carbon you put that hydroxyl group on, that's carbon 1, no matter what. It is what it is. So from there, this is being added to hydrogen chloride. There's your hint. It's a hydrogen halide. There will be a swap out between the hydroxyl group and the halogen. These 2 will switch places. We then have our same cyclopentane structure, but now a chlorine coming off of there, plus HOH. If you wrote it as H2O, that's fine. It still distinctively is water. We do not need to specify where that chlorine group is because it is assumed is on carbon 1 in the cyclic structure. Chloro, don't forget the word cyclopentane. There it is. chlorocyclopentane and water, predicted products for the substitution reaction. Alrighty, once again, these questions do not actually practice the reactions. They practice combustion and doing some calculations and doing some drawing naming, and the real stuff with the reactions and differentiating between them will happen after the third podcast. Good luck, guys.